begin with a word of prayer. So, dear Father, we thank you for this day. Again, Lord, I thank you for these students. Just pray you to guide our thoughts today and just help us to glorify you, what we do, Lord. In your name I pray. Amen. So, so we started looking at this algebraizability of planar vector fields paper a little bit last time. And I think that's really neat, and I want to know more about it, but I haven't had a chance since Monday to dig further into it, so I'm thinking I'll save that for next time. And so what I'm going to do today is just to continue trying to just give some examples in the differential equations over an algebra material that Nathan and I found. And so I'll start with that example that we got cut off last time, because it says a lot. This example says a lot, really. In particular, we want to solve w prime prime minus w equals to 0, where w dw dz is my w prime, right? And I'm assuming that w is a function from the hyperbolics to the hyperbolics, basically. So we're solving this differential equation over the hyperbolic numbers, namely our direct sum jr, right, with j squared equal to 1. So if you, first order of business is you could just try to do the things we usually do, right? So in fact, I'll even go through a little bit of the backstory here, right? So if you let w equal to, say, e to the lambda z, right, then w prime is lambda e to the lambda z by the calculus that we've looked at, and w prime prime is lambda squared e to the lambda z, right? So if this is going to be a solution to that given equation, what you'd need then is lambda squared e to the lambda z, right, minus e to the lambda z equal to 0, which, as usual, gives us lambda squared minus 1 times e to the lambda z equal to 0. This is pretty standard, really calculus 2 kind of stuff. Well, we don't cover second order stuff in calculus 2. There's a lot of universities that cover constant coefficient second order ODEs in their second calculus course. It's not unusual. At least NC State was doing it when I was a grad student. So the exponential is non-zero over an algebra. So the only way for our guess, this is a guess, right? The only way for our guess to work is for lambda squared minus 1 to be, 0. But if we think of lambda as being a hyperbolic number, there's a lot of solutions here, some of which are not familiar, right? So we have, if you think of f of t to be t squared minus 1, right? Well, then you can see that f of 1 plus or minus 1, right, is 0. But also f of plus or minus j is 0, right? I mean, or to be less weird, I mean, this says solutions lambda equals to 1, minus 1, j, and minus j. All right. But here's the thing. And so what are the usual homogeneous solution stuff still works, right? The sum of solutions is still a solution. Hyperbolic linear combination of solutions is still a solution. If I could use the projector, I've lost my adapter. I can't project at the moment. Nathaniel has been letting me borrow his Lenovo ancient machine that still has a VGA jack to project in Calculus 3 at the moment, but I gotta find that stupid thing. Anyway, all of these are ancient rooms, they've all got, they don't have the HDMI, they've got the, Anyway, the theorem that I have proved, and I can't project at the moment, is that if you look at a nth order, well, I have an existence and uniqueness theorem, all right? And my existence and uniqueness theorem, a corollary to it really, says that if we look at an nth order non-degenerate, an nth order sort of not weird, AODE, which this is an example of, then there must exist a fundamental solution set which is made of n linearly independent in the hyperbolic sense solutions, right? So that's a theorem I have. Theorem. If if L of W equal to 0 is non-degenerate nth order AODE, then there exists a fundamental solution set W1, W2, Wn, which is linearly independent over A. It's not real linear independence I'm talking about. It's a linear independence. It's linear independence with respect to the A module. In other words, if you have CW1 plus C2W2 plus plus CNWN, where C1, C2, Cn are elements of the algebra, if that's equal to 0, well, that implies that C1 through Cn is 0. That's the kind of linear independence I'm talking about here. It's a linear independence with respect to the algebra. All right. So I have a proof, which I'll try to show you guys sometime. It's by far the most technical thing I've proved in anything here. It's currently submitted to a referee somewhere. I hope it doesn't have an error. But and the proof is an adaptation of the usual existence uniqueness theorem, which is based on something called the Picard iteration. And I was able to take the usual thing, which is done with a real integral, and replace it with an integral over the algebra, and prove the usual sort of convergence of the Picard iteration, which ultimately gives me the existence of a unique solution to the initial value problem. And then more or less the same arguments that you go over if you read them, or if you don't, in the usual differential equations follow through. Like once you have the existence and uniqueness theorem, then you get, that allows you to build the fundamental solution set and so forth. But well, anyway, I'm not, this is actually not the fundamental theorem, but it's a theorem that I want to use in here. The point is, I happen to know this from, or theoretical algebra independent arguments for a commutative associative finite dimensional algebra. If I look at a nth order non-degenerate AODE, then I get a fundamental solution set, actually. So the question is how to find it. That's mostly what I want to talk about today, is how do we find fundamental solution sets. You see, this is embarrassing. This example already is embarrassing. It's troubling, because this is a second order differential equation, right? What did I just find? I found 4 distinct eigenvalues, if you will, right? And each one of those gives me a solution. So I've got like W1 is e to the z, right? I've got W2 is e to the minus z. I've got W3 is e to the jz, jz. W4 is e to the minus jz. Yeah.
How much does that really mess with, though? I mean, what if we're given, like, say in substance we're given, like, initial values? Like, that really doesn't screw with much, because, I mean...
But it would seem to contradict my theorem. I just found 4 solutions to a second order problem. And they have distinct exponential arguments, right?
So you're saying the theorem's wrong, or the problem has some sort of hidden...
So, check this out. The determinant of e to the z, e to the minus z, e to the z minus e to the minus z. This would be the, what, the Wronskian, right? Of e to the z, e to the minus z at z, right? Yeah, that is, what is that? That's equal to minus 1, which is minus 2, which is not equal to 0. Very true. Well, this says that, what this tells me is that e to the z comma e to the minus z is a linearly independent set of functions over the hyperbolics. I haven't said more. What happens if we look at something like e to the z, e to the jz? What's that? So, by the way, what's the usual derivation for the Wronskian? If you have this is equal to 0, right, then that says right, and so forth and so on down the line. Good grief. Which suggests that the matrix, right, formed by W1 this, the Wronskian matrix has to be what? The determinant of that matrix, I think it has to be non-zero. Yeah. Well, that's the thing is, if you want to be careful here, we're not looking at an equation. We're not looking at a system of equation over the reals. Those coefficients, the C1 through Cn, those are algebra. So we're outside the bounds of what you guys know. We're asking the question, how to solve a system of n equations and n unknowns, where the unknowns and the coefficients are taken from a ring with zero divisors. The things you learned in 422 don't apply here. It's not a principal ideal domain. It's got zero divisors, possibly. It turns out that, oh man, now I'm a little bit rusty now. Curses. Trying to think here. It could be that that's non-zero and still problematic. If that determinant works out to a zero divisor, it's not good news. So what you need, if I remember right, I should have read more before I talked to you guys today. I'm sorry, but I believe if this is an element of the units, right, of the algebra, right, which I have been denoting a upper x, but I'm about to have a change of heart on that. I think I probably should use u of a. I should probably use u of a for the units of the algebra, and I should probably use a sub x for the non-zero elements, so I can distinguish. Because, in a field, it doesn't matter. The units of the field are the non-zero elements. But when we're working over an algebra, there's a distinction between the non-zero things and the units, because non-zero also includes zero divisors. But anyway, whatever the notation is, if that's a unit, then we're okay. Then that implies that that matrix is invertible, and consequently, Consequently, you can solve the system of equations above uniquely for the zero solution, which is what we need for linear independence. Now, if that determinant works out to a zero divisor, the larger point is that formula for the inverse of a matrix. Do you guys remember the formula for the inverse of a matrix in linear? Like, what's M inverse equal to? It's 1 over the determinant, right, times the, we call it the adjugate or the classical adjoint of M transpose. This formula continues to make sense over a commutative ring, provided, of course, that this makes sense. In other words, that the determinant's a unit. Its multiplicative inverse exists. So this formula fails when the determinant's a zero divisor. And in fact, in that case, when that matrix has a zero divisor as its determinant, it will permit non-trivial solutions. This is known as well. Infinitely many, in fact, in our context. So these things were proved by McCoy back in like the 40s or 30s. I have a book called, I have a book just on, like matrices over commutative rings, and it has proofs of all this stuff in there. The courses are taught at this in various universities in the East, I think. The book seems to be fairly popular. It's cheap. I don't think these things are widely known in our universities, though, as far as I know. Maybe I'm just the wrong universities, but this guy. So let's continue with this. So trying to make you guys aware of some issues here. Don't worry, the theorem is fine. The error is in my interpretation. So I'm just trying. I'm letting you experience my week of angst, because there was a week I suffered under this. How can this and this both be true? Right? Because these are distinct, right? Wrong. These are not linearly independent, is the thing. They have distinct arguments, but they're not linearly independent. So what's this one work out to? J e to the j plus 1 z minus what? E to the j plus 1 z, right? Uh-oh, that is j minus 1 e to the j plus 1 z. Which, by the way, simplifies. So think about the exponential. It's 1, then j plus 1z, j plus 1z squared over 2, so forth and so on. Anytime you hit j minus 1 with j plus 1, they vanish. So the only thing that remains in the exponential series is just the first thing. So this is exactly equal to j minus 1. Which speaks to the fact that these are not independent over the hyperbolic numbers. They have different exponential arguments, but they are not linearly independent. Distinct arguments for exponentials does not imply independence over an algebra. Something else. So, you're like, I don't believe it. Show me how they're dependent, right? So can we find that? How is it that we can combine? How can we find an algebra constant C1, right? C1 times e to the z plus C2 times e to the jz equals to 0. How is that? How can we arrange that to happen? It's actually not possible with C1 and C2 being real. They are independent in the sense of real algebra. The linear dependence comes in the sense when we consider them as an H module. Yeah, sorry. All right, so I'm trying to remember how I found these. Do you guys have any ideas? Yeah, I'm trying to remember how I actually ended up calculating Stupid thing. Here, let me cheat. Let me cheat if you don't mind. Huh. That's funny. I'm not, huh. Do. Well, I have this in the paper. This is equation 64 in the version I have posted on the archive, 1708 04137 version 1 from August 2017. I posted this in August. Good grief, that's a while ago. Introduction to Theory of AODs, that paper. Anyway, equation 64, I observe the following. I say short calculation reveals. I think I found this stuff with Audrey, I should say, for her honors project. Once upon a time, e to the z plus 1/2. It was like right after the final in abstract, a year or two ago. Not last year, but the year before. So this is one identity, which is true. For the life of me, I can't remember the short calculation. It's really bothering me right now. I mean, I worked this out. Why did I do it? Clearly you've got what? Maybe you're right. Maybe it's Koch-Cinch stuff. Let's go that path, right? Try it that way. So I'll work on this side since it's the complicated side, right? So in terms of Koch and Cinch, what is this? This is, oh gosh. I'm not sure that really helps. Yeah.
The other side's cosine.
Stink. How did I? I'm gonna leave this here for a second. Let's just consider the linear independence things. There is something I can show you over here to show you what conditions necessary for linear independence of exponentials. Let's go that path. And then while I'm doing that, something will free in my mind, and it'll let me to tell you what I'm forgetting there. Okay? I'm buying some time. Let me buy some time while I shake that loose. So check this out. So if we have, consider e to the lambda 1, e to the lambda 2 z, e to the lambda n z, right? I want those to be linearly independent. What do I need? Well, I need c1 e to the lambda 1 z, right? Plus c2 e to the lambda 2 z. Cn e to the lambda n z equal to 0, right? To imply that all the constants are 0, right? So, if I multiply that by, say, well, I can, multiply by, let's multiply by e to the minus lambda jz, lambda sub j. Oh, fine, not sub j. Lambda sub I z. There, you happy? All right. Then what happens? We've got, oh, that doesn't help. I'm an idiot. Curses. I mean, that will isolate the c sub I that doesn't directly help. Do I actually have to calculate the Wronskian? Is that how I did it? Yeah. All right. Apparently I'm not capable of doing this either. Let's start out smaller. How about e to the alpha z, e to the beta z? Let's set our sights really small. I want to show those are linearly independent, right? And so I want c1 e to the alpha z plus c2 e to the beta z equal to 0 to imply c1 and c2 are 0. So I differentiate, right? Gives me that. And so when I look at the, so I'm really just kind of, what am I doing at the moment? I'm just working that Wronskian thing out again in this specific example, right? Sorry to be redundant. So I need this matrix to have an inverse because I need it to only give me the 0 solution, right? So what is the determinant of this matrix? It's beta minus alpha, right, times e to the alpha plus beta z. Now, the good news is that the exponential is always a unit, because exponential of anything's inverse is just exponential of the minus argument. Yeah. So really the question is just, is beta minus alpha a what? We need beta minus alpha as a unit. So this will be an element of the units of A, provided what? If we're given that beta minus alpha is an element of the units. So the arguments have to differ by a unit. In other words, the arguments cannot differ by a 0 divisor or 0. So in a field, this condition just reduces to what? Right. So in a field, it suffices to say that exponentials are linearly independent if their arguments are distinct. But over an algebra, something weird happens. We can have exponentials with seemingly different, I mean, they are different arguments, and yet the exponentials are not linearly independent. That said, I have forgotten how I derived these things. I mean, I also have the formula e to the minus jz, right, is equal to 1/2 of 1 minus j e to the z plus 1/2 1 plus j e to the minus z, I think. Yeah. If you take these and you add them, what do you get? Oh, I don't know. But that's not what I need. I mean, I think I just seen, I didn't know that, I don't remember this. I was hoping that this would still be non-zero. I'm a little disappointed in this calculation. I was expecting that this was not, I was not expecting that this would fail. I thought it was okay to mix one exponential and one e to the plus or minus j, but apparently not. My intuition's wrong. I'm pretty sure that if we use e to the j and e to the minus jz, that's okay. In the sense that if we do e to the jz, right, e to the minus jz, differentiate, we get j e to the jz minus j e to the jz. What happens when you calculate the determinant of that thing? Minus minus, right? So we get minus j, we get minus 2j, which is no problem. That's a invertible hyperbolic number. So that says e to the jz and e to the minus jz form a solution set, a fundamental solution set for this problem. E to the z, e to the minus z form a solution set for this problem. But if I take one exponential and one e to the jz, that's not a solution set because there's some linear dependence. But I can't figure out what that linear dependence, I mean, I've worked this out before, you know? I mean, if you plug in z equal to 0, you can see it works, right?
I mean, I just tried plugging in like the first and second, both black
Uh-huh.
other things, and by direct calculation, I found that C1 is equal to a complex number multiple of C2. C2 has to be 0.
So you want to just attack it directly?
I mean, yeah,
This one? Okay, let's try. Good idea. So,
it doesn't work at non-zero because at the same time C2 is forced to 0 by equating.
let's see here. So A1, I mean, just let me get it all out on the table here. A1 plus JB1. Now, so we're going to work down to the level of real notation, right? That's the plan? So e to the z is e to the x plus jy, which is e to the x cosh y plus j e to the x sinh y, right?
To make it easier, can we just let C1 equal to some random well, just make it tinier? No, would it make a difference, will it? Just for now.
Well, that's the thing is you might want to divide by C1, but you can't. I mean, I guess I could try to do a matrix calculation. We've got e to the z. We've got e to the jz here, right? We've got e to the z and e to the je to the jz down here, all right? And you can do row operations to these. They're just, I mean, we can do row operations. This is what? I would do row 2 minus row 1, right? Zero, right? And then we get what? J e to the jz minus e to the jz, yeah? So this, as you can see, becomes, and we can multiply the first row by e to the minus c. That's allowed as well, right? That's a unit. So you can. What are the rules for doing row operations over a ring? It's pretty much the same as for vector spaces, except you gotta. It's not. You can't. If you don't want to change solution sets, you can only multiply equations by units. Multiplying equations by zero divisors is forbidden. So once you've got a zero divisor sitting in a pivot position, you're kind of up a creek. Like you cannot reduce it so it's all leading ones. No can do. Not usually. But we get this. Ooh, cool. Look at that. That's kind of snazzy. J minus 1. Hey, why don't I believe in linear algebra? I should believe in linear algebra, right? Linear algebra believes in me. Let's see here. J minus 1. Sorry, kind of giddy after. It's my fourth class for the day. The density of stupid things that I say increases. So, right? That's it's kind of about as far as you can go. What does that mean in terms of the original system of equations? The original system of equations was what? C1 e to the z plus C2 e to the jz equals to 0, and differentiating it, C1 e to the z plus jC2 e to the jz equal to 0. Sorry to ignore you, Jess. When you said complex numbers, I don't know what that means. Like, you're saying something about complex numbers, and like, I don't know. I mean, Oh, maybe you meant hyperbolic. Maybe I just misheard. Okay, so maybe we'll get the same thing anyway. Ah, Bowser. So what we got? You know, there's a row. There's zeros here, right? The augmented matrix. So this one says what? This says C2, right, times j minus 1 e to the jz equal to 0. And the first one says that C1 plus C2 e to the j minus 1 z equal to 0. So this suggests what? This suggests that, well, this is a unit, so you can ignore that. What this says really is that C2 has to be equal to some constant. Essentially, C2 is some constant. I don't care. Let's just say C2 possible solution. All right, a possible solution. C2. That says C2 is j plus 1. Once you know that C2 is j plus 1, we get that C1, right, is equal to minus C2, well, minus j plus 1, right, times e to the j minus 1, z. Hey, but that's the calculation we just did a second ago. This and this are natural enemies. They just leave the constant term in the exponential. So that gives me that my C1 is actually what? It's actually just minus j plus 1. Oh, there it is.
I had the equations, but it didn't occur to me. I keep forgetting that C2. I thought there was only a 0 C2 that was for C2 times j minus 1 is equal to 0. But we forgot that.
Ah, you forgot the yeah.
I had that equation. I had that, and then I had
It's
one that said
ah.
hyperbolic multiple.
So you were close to this. Then you got to exploit this. This is the new thing. This is the thing that's so foreign to our experience working over fields. Is everything is about the zero divisors, almost everything. So long story short, we've got minus parentheses 1 plus j times e to the z, right? Plus what? Plus 1 plus j. Really? Plus 1 plus j times e to the jz, allegedly is 0, huh? This is what the math seems to have just told me. Is that true?
Yeah, it is. Because 1 plus j times that formula over there would cancel out. Because zero divisors, 1 plus j, 1 minus j.
Oh, so this is really 1 plus j times what?
The e to the jz is that formula you have there.
E to the jz minus, I mean, this is 1 plus j times e to the jz minus what? E to the z, right?
But you have that formula for e to the jz, which has a 1 minus j, so you can multiply that.
Ah.
It's going to give you 0 on the negative z. And then the
Oh,
one
I see what you're saying. You can see it from my other identity. Right. There's probably a direct way of seeing it as well, but your point is well taken. So this, it picks up two pieces, right? So this piece automatically gets killed with that. And then the other piece, 1 plus j. Oh, so then that conspires to create another 1 minus j after the cancel. Okay. Yeah. There's probably a way to see this also in terms of direct manipulation of e to the jz. Is that something nice? I mean, maybe not. It's not, Huh. Funny. Of course, when you're trying to prove an identity like this, if you don't see anything right off, a good technique here is to just differentiate it, show that the derivative is 0, and show that it's constant, right? If you call this thing, say, g of z, right? What's g prime? Right? Which is what? That might not help so much, actually. That's j plus 1 e to the jz minus 1 plus j e to the z. I feel like I'm going back to where I started. This is look at this thing. That's just not friendly. Look at that. That's G again, right? Oh, weird.
I guess that's zero divisor. Plays around just to make it.
That is not nice. But this is not an, if I get dgz equals to g, this makes me want to say that g is equal to e to the lambda z for some lambda. Is that e to the lambda z for some lambda?
So that's surprising. We're dealing with exponentials, so isn't that kind of one of the properties of exponentials that we love? The fact that it's kind of
Right.
it's helpful in some way, like that can't be.
I'm not saying this is wrong. I'm just saying it's weird that my usual technique to differentiate something so the derivative is 0 and then plug in a value to show the identity holds is just gone full circle on me. Didn't help at all. All right, well, anyway, let me stop belaboring the weirdness. The larger point is that, in fact, we did find a fundamental solution. The trouble is we found several different ways of assembling it. All right, you can either use e to the z, e to the minus z, or you could use, e to the jz, e to the minus jz. And in fact, in terms of my observation here about the difference of the arguments being a zero divisor, it makes sense that I couldn't use e to the z and e to the jz, right? What happens if you take the difference? Like this has got lambda 1 equal to 1. This is lambda 2 equal to j. What happens to the difference there? The difference is 1 minus j, and that's the trouble. So. All right, let me I'll show you guys an example here. So that it took me a while to wrap my mind around what was going on here. I finally, because I really thought for a while I struggled. I thought that my theorem was wrong. I thought the existence and uniqueness theorem had some kind of, really subtle and just, insidious error somewhere. And I really doubted it for a day. And then so much so that I tracked Daniel Fries down wherever he was at the point, and I was like, Daniel, could you read the proof again? I feel like there's something wrong with it, but Daniel emailed me back. He's like, no, I've checked it line by line. I don't see anything wrong. I was like, well, if Daniel doesn't find anything wrong, it's probably okay. And it was okay. It was my understanding of linear independence that needed work. Okay, so here's another example that'll throw you for a loop. And I really, really like this example. I think this example is just absolutely beautiful. And the techniques I know will work over 3 hyperbolic or 4 hyperbolic or null numbers or anything. But for the most part, my examples are in the hyperbolics just because I found a lot of interesting stuff there. So, So here's another one. Yes. This is my example 5.8 from the paper. And so here I'm considering, I'll write it in differential notation, d minus 1 times d minus j. All right? So this is in here, of course, d is just notation for d dz, and still in the hyperbolic numbers, right? So you can easily observe that e to the z, right, and e to the jz are solutions. It's still the case that differential operators commute over the algebra, like so the things we do in differential equations about commuting operators, those calculations still hold true here because the calculus is the same. So, if I hit this, if I plug in e to the jz here, I get j e to the jz minus j e to the jz, so this works out to 0, and then feed 0 into d minus 1, still get 0. And vice versa, if you feed the e to the z into that first, that's 0. And so, anyway, these are both solutions. Hey, we could even write it out. What would this be in the prime-prime notation? This would be what? W prime-prime minus what? 1 plus j w prime plus jw equal to 0. There's the differential equation in the other notation, right? So here's my intuition for what's going on. If I want to find a differential equation which really shows me new behavior, something which is bizarre from the perspective of studying differential equations over fields, if there's a zero divisor just sitting there staring at you, odds are whatever happens in the solution to this are something maybe you've never seen before. And in fact, that's what's going to happen. You also see that this is weird in the view of the Wronskian, right? Because if we look at the Wronskian of e to the z and e to the jz, as we just worked out, what do we get? We get j minus 1, right? So these are not linearly, so these are solutions, yes, but they're not linearly independent solutions, right? So that begs the question, right? Son of a gun, would you look at that? That's very annoying. Look at this, guys. This is very annoying. Notice 1 minus j e to the z plus, who wrote this paper? 1 plus j, you'd think I hired somebody to write it or something, e to the jz is equal to 0. Which I think I just erased. That is not quite what I wrote, though, is it? Huh. I say that's the explicit dependence. Now I wonder if we made a mistake earlier. I mean, I guess there could be more than one way to write the dependence, possibly. I'll have to look back at this later. I'm a little bit... Kang's not here. We should make him figure it out. Right? All right.
It's kind of like bringing, I thought, kind of our goal is to look at differential equations and kind of like a real sense, at least equations, and then try and find like an algebra home in which we could solve it.
Oh,
Why are we proposing the hyperbolics at first in the differential equation? Because doesn't that kind of fix our...
Oh, no. So I have turned the page. I'm not looking at the inverse problem right now. What I'm doing right now with you guys is I'm trying to explore how do we solve differential equations over an algebra. We're building a machine. This is the machine that we hope to be able to then attach to the inverse technique later to solve PDEs in novel ways. But, if I can convert PDEs to an algebra differential equation and I don't know how to solve those, or I don't know how to understand those, to analyze them, then my inverse problem isn't very useful either. Of course, again, I do think the inverse problem is harder than what I'm doing right now, but yeah, one step at a time, I suppose. Okay, so I don't know if you guys remember this or not, but when we have operator factorization, we can use substitution as a solution technique, right? So let me remind you how that goes. We let eta equal to d minus j acting on w, right? Then my initial equation star, right? What's it become? This is a standard differential equations technique, right? If you have an operator factorization, you can solve by substitution, and you can reduce the order by just, if you have linear operators L1, L2, Lk like that, y equal to 0, what you do is you just call all of this stuff eta. Well, not even 0, h, whatever, and you solve L1 of eta equal to h. You get a solution, and then you face the music. That solution is then equal to L1, L2, and then you keep doing this. You can unsubstitute. Basically, if you have an operator factorization, you can solve the differential equation by repeated integration in a very systematic way. I do not teach this in differential equations anymore. Once upon a time. But anyway, okay, so what do we face? We face this guy. Can you solve that? This we can solve, right? This is nothing more than eta equals 2, like c1 e to the z, right? Yay. So then what do we have to solve? We have to solve, what was eta? So now we've got dw dz minus jw equal to eta, which is c1 e to the z, right? So we got to solve that. So how do you solve such an equation? Integrating factor technique, right? That's a linear. So what's the integrating factor? Multiply by what? I think we should multiply by e to the minus jz, right? So that will give us e to the minus jz dw dz minus j e to the minus jz w equal to c1 e to the 1 minus j z, yeah? So the larger point here, guys, is because the distinct solutions to the characteristic equation differ by a zero divisor, I only get one exponential solution, like just plain old garden variety exponential solution. So I'm missing another solution from the solution set. The question is, what does that look like, right? In the ordinary real case, when they're a repeated root, you know what we do. If I've got like lambda minus 1 squared, we get an e to the x and then x e to the x, right? So what's going to happen here? What is it? Is it the 1? Is it the j? I mean, how's it going to go? That's what we're kind of wondering. Now this, of course, integrating factor, d dz, right, of e to the minus jz w is equal to c1 e to the e to the 1 minus j z. So you integrate both sides, right? How do you integrate c1 e to the 1 minus jz? How do you integrate e to the az? What do? You know what you do. You do 1 over a, e to the az, plus c2, right? But what's the trouble here? My a, so 1 over a is forbidden, right? This exponential, you cannot integrate by elementary means. So how do you integrate? So that is the integral of parentheses 1 plus the summation n equals 1 to infinity of 1 over n factorial 1 minus j to the n z to the n dz power series. It's always the way around. And remember that paper by Daniel proves that this term-by-term calculus is legit. So that works out to, write it down here. Ow! Let me write it over here. So we get e to the minus jzw equals to a constant plus z plus the sum n equals 1 to infinity of 1 minus j divided by n minus 1 factorial times n plus 1 times z to the power n plus 1. So, and I could call that, I should probably, well, where did my C? I had a C1 somewhere. I think I lost it. I think I'm supposed to have C1. Yeah. Sorry, I think I lost that. Let's see here. So that one integrates to a z, right? So this should be, so C1's out here, right? And we got C2, let's say. The C2 is from the integration here, this integration, right? And technically that would multiply the C1 in that way. And then let's solve for w. Well, w is C1, C2, e to the jz, plus C1, z, e to the jz, right? Plus, well, this plus the sum, n equals 1 to infinity of 1 minus j over n minus 1 factorial times n plus 1, z to the n plus 1. So, you know how things go. We might as well just call this thing what? C2, right? Yeah. Or C1 tilde or C2 tilde, whatever. Anyways, it's just a constant. No. But does it make sense intuitively? Like, what's going on here? So we have, what do we have? We have our constants, our characteristic values here were lambda were 1, and lambda 2 was j, right?